Dear students, in this video we are going to see Mersenne primes, Fermat's little theorem, and then Carmichael numbers. Now you see here, what is Mersenne prime? Mersenne prime is a prime number of the form 2 power n minus 1. Okay, this is called Mersenne prime. Okay, here what is n? N must be a prime number. Okay, suppose n is 2. Then 2 power 2 minus 1 is equal to 3. See, 3 is a prime number. Then put n is equal to 3, you will get 7 as a prime number. So if we put n is equal to 5, then 2 power 5 minus 1 is equal to 31. So similarly here, when we put n equal to 7, we will get 127. See, these numbers 3, 7, 31, 127 are called Mersenne primes. Okay. See, suppose if we put n is equal to 4, 4 is not a prime. Suppose if you put a composite number for n, that is n is equal to 4 here, then 2 power 4 minus 1 is equal to 15. It is also not a prime. So what we have to put here, we have to put any prime number for n in this form 2 power n minus 1, and we will get the Mersenne primes. That's it. Now you see Fermat's little theorem. What it is, if p is a prime and if a is any integer, then a to the power p congruent to a modulo p. In particular, if p does not divide a, then a to the power p minus 1 congruent to 1 modulo p, where a is vary from 1 to p, which means 1 less than or equal to a less than p. Here we see the examples. Now if p is equal to 3 and a is equal to 2, now you can see here p does not divide a, which means 3 does not divide a. Okay, therefore we can write this a to the power p minus 1 congruent to 1 modulo p. That is, a is 2 here. So 2 to the power 3 minus 1. So 2 to the power 2, that is 4. That is congruent to 1 modulo 3. Okay, here p is 3. Okay, similarly, if p is equal to 7 and a is equal to 4, we can write a to the power, that is 4 to the power 7 minus 1 congruent to 1 modulo 7. Here p is 7. So here we write. So here we write 7. Okay. Now here we see this example. Find 7 to the power 2019 modulo 13. Use Fermat's little theorem. Okay. We have to compute this value 7 to the power 2019 modulo 13 by using Fermat's little theorem. Okay. Now you see here, in particular, if p does not divide a, then a to the power p minus 1 congruent to 1 modulo p. Now here, what is a, what is p? Now see, this is a, this is p. Now in this question, p is 13. See, this is p is 13. Okay. Now what is a? 7 is a. Okay, we can say that 7, a is 7, p is 13. P does not divide 7, means 13 does not divide 7. Okay, so that by Fermat's little theorem we can write, you see here, a to the power p minus 1 congruent 1 modulo p. Now here a is 7, so 7 to the power 13 minus 1, that is 12 congruent 1 modulo 13. Okay, by Fermat's little theorem we can write here this one. Okay, now you see here the degree of 7 is 12. Okay, now what we write? We write 2019 is equal to 12. This number 12 multiply 168 plus 3. Okay, here what I am getting by Fermat's little theorem, I am writing 2019 is equal to this number multiply some number plus remainder. Okay, so now we can write 2019 is equal to 12 multiply 168 plus 3. Okay, now you see here 7 to the power 2019, that's what we require. 7 to the power 2019 modulo 13 we require. Okay, now 7 to the power, see this here I am going to substitute. Okay, now 7 to the power 12 to the power 168 I can write. Okay, here 7 to the power 3 multiply 7 to the power 3, here base is same, so that I separate here 7 to the power 12 whole to the power 168 multiply 7 to the power 3. Okay, now what is 7 to the power 12 modulo 13? See here 7 to the power 12 congruent 1 modulo 13 by Fermat's little theorem. So that for 7 to the power 12, what I can put for this, what I can put 1, I can put 1 by using this result. Okay, now 1 to the power anything is 1. Now 1 to the power 168 we have, so definitely that is 1. Okay, so that's why this value is 1. So 1 multiplied 343 is 343. Now apply the modulo 13 for 343. So what is the remainder? That is 5. So this is your answer when we require 7 to the power 2019 modulo 13. The answer is here. This is the answer. So 7 to the power 2019 modulo 13 is nothing but 5. That's it. So here what I've asked in the question, we have to find 7 to the power 2019 modulo 13 by using Fermat's little theorem. That's what we have done here. The final answer is 5. Okay. Similarly, we can do so many, we can practice so many questions which I given in the practice set questions. Okay, that's it. Now you will see here Carmichael numbers. What is Carmichael number? A composite integer n that satisfies the congruence b to the power n minus 1 congruent 1 modulo n for all positive integers b with GCD of b comma n is equal to 1 is called Carmichael number. Okay, now what are the Carmichael numbers we have? 35, 77, 143, 165, 187, see, etc. Here we have so many Carmichael numbers. Okay, these are the few Carmichael numbers. Okay, now see here what is given in the definition of Carmichael numbers. Actually, we take the composite integer n. Okay, what is composite number? Composite number means a number that has more than 2 factors called composite numbers. For example, you see here the factors of 8 are 1, 2, 4, 8. So that we say 8 is a composite number. Okay, because 1 multiply 8 equal to 8 and 2 multiply 4 is 8. Okay, now you see here few examples. See, you take the number 32. What are the factors? You list the factors in the second column. 1, 2, 4, 8, 16, 32 are factors of 32. So that this number 32 is called composite number. Now you see here 43. What are the factors of 43? 1 and 43. So this is called prime number. Okay, these are the few examples for composite and prime. Actually, we have discussed prime numbers in first lecture, but here just we have to know exactly what is composite number. That's why I'm giving these examples. Okay, see here what is Carmichael number? We take a composite integer n that is satisfying this congruence equation for all positive integers b. We don't know what is b. It be any positive integer with this condition: GCD of this b and n is 1. Then we can conclude that this is called Carmichael number. N is called Carmichael number. Okay, now here we will see one question. Show that 2821 means 2821 is a Carmichael number. Okay, now see what is the definition Carmichael number. See, a composite integer n. Okay, here n is a composite number first. Then GCD of B and N is equal to 1, and this congruence is satisfied by N. We can conclude that N is a Carmichael number. Now here you see how we start the proof. Since 2A21 is equal to 7 multiplied 13 multiplied 31. Yes. So we can say that 2A21 is a composite number first. Okay. That is what here given in the definition also. Okay. Now it is a composite number. Yes. Because this number has more than 2 factors. So that 2A21 is a Carmichael. Sorry. 2A21 is a composite number first. Okay. Now see here, the GCD of B comma N is equal to 1. This is the condition for this. Okay. Now if suppose we assume that GCD of any number B, we don't know that what is B. B is any integer. Okay. Now see here what is given. B is any positive integer. Okay. So now B is any positive integer. So that we assume that suppose GCD of B, any positive integer, and 2A21 is equal to 1, then we can say that GCD of the same number B, actually we don't know which number that is a positive integer. Okay, so GCD of B and 7 is equal to 1. Why? Because this is true. Suppose we assume that this is true, GCD of B and 2A21 is equal to 1, then we can write GCD of B comma 7, because we write 2A21 as a multiple of 7, 13, 31. So that we can write this, and GCD of any number B comma 13 is 1. Similarly, GCD of any number B comma 31 is also 1. Okay. Now what Fermat's little theorem says, you see here, see first you take this from this one. By Fermat's little theorem we can write this. Why? Because you see here, if P does not divide A, then A to the power P minus 1 congruent to 1 modulo P. Now here this is the P, value of P. So now modulo 7, see modulo 7, B we don't know. So B to the power 7 minus 1 by Fermat's little theorem, and by using this idea I can write this first equation. So B to the power 6 equal to, why I write B to the power 6? By Fermat's little theorem, B to the power this number 7 minus 1. So that's here I written. So congruent to 1 modulo 7. Similarly here from the second equation I can write this. Yes, by Fermat's little theorem. From third equation I can write this. Okay. Now we obtain for n minus 1 is equal to 2A20. Why? Because to prove that n is a Carmichael number, we have to show that B to the power n minus 1 congruent 1 modulo n. So now here n is this value 2A21. So now what is n minus 1? So we have to calculate n minus 1, 2A20. Okay. Now see, we have to conclude that B to the power n minus 1, that is here we don't know B to the power n minus 1 is 2A20. So B to the power 2A20 is equal to B to the power, see here take the first value 6. So you write 2A20 as a multiple of 6. So that 6 multiply 470 is equal to B to the power 6, this whole power 470. Okay. So congruent to this value is 1. B to the power 6, see here, B to the power 6 is congruent to 1 from this first equation. So now from this first equation I can write this. Similarly, see here, second, B to the power 2A20 is equal to, now you write the same number 2A20 multiple of 12, because here I have 12. Okay. So now 12 multiplied 235 and this one. So now from the second equation we can write B to the power 12 congruent 1 modulo 13. So here for this put the value B to the power 12, we can write 1. So here 1 modulo 13. Similarly, now